The James Webb Space Telescope, a creation of unprecedented power, able to capture the faintest light from the farthest reaches of space. An eye on the universe, it reveals galaxies born billions of years ago, nebulae teeming with new stars, and mysteries from the dawn of time. But for all its power, Webb is fragile. Designed with precision beyond anything we've attempted before, it depends on a delicate balance to do its job. The instruments on the James Webb Telescope must be kept incredibly cold. Frigid. Colder than the coldest places on Earth. If even a whisper of warmth reaches it, these stunning images are lost. So, to protect these delicate instruments, Webb is perched at an exact spot in space, a kind of gravitational sweet spot, where it can hover in a stable orbit, shielded from heat and able to look deeply into the universe. But this perfect position, the precise balance that keeps Webb stable and its instruments cool, depends on principles discovered over 300 years ago. It owes its existence to an age-old puzzle that began when one man, staring at the night sky, wanted to know something very simple. Where would the moon be? The year is 1687. Isaac Newton, the man who defined the laws of gravity, is facing a challenge. He's cracked the code for how two bodies, say the Earth and the Moon, pull on each other. It's simple, elegant, predictable, but add a third body like the Sun, and suddenly everything changes. Newton wants to know where the moon will be, not just tonight, but next month, next year. But the Sun's pull on both the Earth and the Moon distorts the path, tugging the moon off course just enough to make its orbit unpredictable. It's a problem of three bodies, the Earth, the Moon, and the Sun, each pulling on each other, creating forces that shift constantly and making simple predictions nearly impossible. Newton's challenge was daunting, but he wasn't about to give up. He saw that he needed something entirely new, a tool that could handle the continuous, ever-changing motion of celestial bodies. So he invented one. Newton called it fluxions, a form of mathematics we now know as calculus. With fluxions, Newton could calculate how objects moved under forces that changed with every instant. Calculus allowed him to break down the moon's motion, letting him trace its shifting orbit as it was pulled by both the Earth and the Sun. For the first time, he had a way to approximate these shifting gravitational forces. What Newton had solved so beautifully for two bodies became a chaotic puzzle with three. The Sun's gravitational influence added an extra layer of complexity, creating ripples and tiny wobbles in the moon's path. These fluctuations, what we now call lunar perturbations, were the first hints of just how unpredictable gravity could be. Newton's calculations revealed that each small shift in gravity from Earth, the Moon, or the Sun caused changes that were impossible to fully predict. These celestial whispers of chaos made a three-body problem seem unsolvable, even with calculus. What Newton discovered was something no one had fully grasped before. With three gravitational forces at play, there was no single predictable solution. With two bodies, like the Earth and the Moon, the orbit was simple, repeating, and stable. But introduce a third body like the Sun, and the orbit starts to bend, twist, and shift with every subtle pull. These small wobbles in the Moon's orbit made its position frustratingly difficult to predict over time. Calculus had brought Newton closer than ever, but he began to see the limits of his tool. To solve the three-body problem fully would require ideas and methods that wouldn't be developed for at least another century. Born in Turin, Italy in 1736, Lagrange was fascinated by mathematics, and by his 20s he had become one of the brightest minds in Europe. He was captivated by Newton's work, but there was one question that kept nagging at him. How could something so fundamental, gravitational motion, be so chaotic? The three-body problem had left Newton scratching his head. Lagrange saw it as an open door, a problem worth solving. But the tools Newton used weren't enough. If Lagrange wanted to tackle this question, he needed something new. So, like Newton before him, he invented it. First, he created calculus of variations. Unlike Newton's calculus, which tracked continuous changes, Lagrange's version could handle complex systems with multiple factors at play. It let him see how small adjustments here and there would ripple through the whole system. In other words, he can analyze how slight shifts in the Sun's position or the Moon's orbit would impact the balance of forces. But Lagrange didn't stop there. He also redefined how to approach Newton's laws of motion. Instead of focusing on each individual force, he created something entirely new, Lagrangian mechanics, which looked at the energy of a system as a whole. With this new perspective, he could simplify complex interactions between multiple bodies, like those of the Earth, the Moon, and the Sun, and make sense of them in a way that Newton's original mechanics couldn't. But not everyone was impressed. In Lagrangian's time, questioning Newton's mechanics was almost heretical. Newton was a legend, a man whose work was, in some eyes, unimpeachable. Yet Lagrange persisted, and with his new methods he found something astonishing: gravitational sweet spots in space. By analyzing the balance of force and energy, he identified 5 points where an object could, theoretically, hover in a stable orbit. They were unlike anything Newton had imagined, places where the push and pull of gravitational forces canceled each other out perfectly. He called them equilibrium points. Today we know them as Lagrange points. But in his own time, few could grasp what he had discovered. Some dismissed the points as mere mathematical curiosities. Yet Lagrange saw something more, an answer to the very chaos Newton had struggled to understand. For over a century, Lagrange's discovery of gravitational balance points remained a mathematical curiosity. They were calculated wonders, but practical use for these points would have to wait until technology caught up. By the 20th century, scientists and engineers began to see the potential in these balance points. What if gravitational sweet spots could become more than a theory? What if they could serve as a cosmic parking lot for satellites and telescopes? The idea was ambitious. By positioning satellites at these points, we could hover in space with minimal fuel, giving them steady vantage points to observe the sun, study Earth's environment, and eventually peer into the depths of space. But until the first mission reached one of these points, they were just theoretical. The possibilities were enormous. Lagrange points scattered around our solar system could offer stable outposts, not only around Earth, but also around other planets. But it would take one bold mission to finally prove that they were more than just an idea on paper. Okay, so it's the 1970s and you're a satellite engineer, and you want to launch a new type of satellite. But here's the thing. You don't want it to circle the Earth, and you don't want to send it to the outer edges of the solar system. You want it to hover in one particular spot to observe the sun. And here's the thing. Gravity. Every satellite that's placed near the Earth will invariably be pulled back towards the Earth. Likewise, any other place you put in space is going to be affected by the gravity of the sun or the gravity of the moon. What you need is a way to balance those forces, a place where the pull of the Earth and the pull of the sun could cancel each other out, leaving the satellite stable in one position. But is this even possible? As you search for answers, you uncover a centuries-old concept, Lagrange points. In this gravitational sweet spot, the forces between the Earth and the sun balance perfectly, allowing an object to remain stationary with minimal fuel. One point in particular stands out, L1. Positioned directly between the Earth and the sun, this point offers an uninterrupted view of solar activity. If a satellite could reach L1, it could monitor the sun's behavior and send early warnings about solar storms. It sounds ideal, but there's a catch. No one has ever stationed a satellite at a Lagrange point before. The idea is risky. In 1978, NASA takes the plunge and launches the International Sun-Earth Explorer 3, or the ISEE-3. The first mission with a goal to station a satellite at L1. But until it arrives, no one is certain it will work. The engineers hold their breath. Will it stay, or will gravity pull it off course? After weeks of careful adjustments, the ISEE-3 finally reaches L1. It holds its position, balancing perfectly between the Earth and the Sun, sending back the first streams of data on solar activity. For the first time, the world sees that Lagrange points aren't just theoretical, they can be real outposts in space. The ISEE-3 success proved that we could use Lagrange points to create stable observation posts in space. Soon after, L1 became a critical location for solar observation missions, including SOHO, which has monitored the sun for over 2 decades. And with each successful mission, the potential for Lagrange points grew. Another point, L2, became a focal point for deep space observation. This point, away from the Earth and in a stable, shadowed orbit, would soon become home for the most powerful telescope we've ever built. Years after ISEE-3, you're back in the engineer's seat. This time your mission is different. You're not just trying to station a satellite. You're building the James Webb Space Telescope, the most powerful telescope humanity has ever launched. This telescope isn't just looking at the sun or the earth. It's aiming to look back in time, to capture the faintest light from the birth of the universe. For Webb to see the distant universe, it needs conditions unlike anything close to Earth. The telescope's instruments must be kept at a cryogenic temperature, colder than the farthest reaches of our planet. Any warmth, even a fraction, could ruin its sensitive readings. So where can you put this telescope? You need a location far from Earth's heat and light, where it can remain steady with minimum fuel. That's when you look at L2, the second Lagrange point. L2 sits at the opposite side of Earth, sheltered in its shadow, with the Earth and Sun perfectly aligned behind it. If Webb can reach L2, it can hover there, balancing the gravitational tugs of both Earth and the Sun. Positioned in Earth's shadow, it's protected from the direct sunlight and constant shifts in temperature. It's ideal for a telescope that needs to stay cool and steady. But that's only part of the solution. Even at L2, some heat will reach the telescope. So you give Webb an extra layer of protection, a 5-layer sun shield, meticulously crafted to reflect and block every trace of heat that could disrupt its readings. The design is groundbreaking, but it's risky. No telescope has ever operated from L2 before, and Webb's sunshield has to unfold perfectly to function. If even one layer fails, the telescope won't be able to reach its frigid operating temperature. You watch, holding your breath, as Webb reaches L2 and begins the delicate process of deployment. One by one, each layer of the sunshield unfurls, snapping into place until the telescope is shielded and ready to begin its mission. With Webb in position, everything is set. From L2, shielded from light and heat, the James Webb Space Telescope has a perfect view into the depths of the universe. Here it can detect the faintest traces of light, capture images from billions of years ago, peering back to when the first galaxies were born. In this sweet spot, Webb is more than just a telescope. It's a time machine, gathering light from the most distant stars and galaxies. Thanks to L2, Webb has the perfect vantage point to see deeper into time than any telescope before it, uncovering secrets from the dawn of the universe. 300 years ago, Newton faced a problem he couldn't solve. Understanding how 3 celestial bodies, like the Earth, the Moon, and the Sun, pulled on one another. Though it seems simple, Newton's own equations failed, and he left his 3-body problem for future generations. 100 years later, Joseph Louis Lagrange picked up the thread, and though he didn't solve the problem, he discovered something extraordinary: sweet spots in space, where the gravitational forces of large bodies canceled each other out. These sweet spots, now known as Lagrange Points, they offer an incredible opportunity because they exist around every planet in the solar system. And they offer the opportunity of placing telescopes and satellites in future missions around places like Mars and Jupiter and beyond in stable orbits. It's humbling to think that our most advanced space telescope is held in place by ideas centuries old. And even with all our modern technology, we still rely on the genius of Newton and Lagrange today. Because centuries ago, Newton and Lagrange, they charted our path through the cosmos with pen and paper. And with all our advanced technology, isn't it amazing that we're still relying on their maps? I just wanted to thank you for watching the video. If you liked what you saw, please like, subscribe, leave a comment. If you didn't like what you saw, really, thanks for watching. Please leave any comments below. Tell me what you liked, tell me what you didn't like, and leave any ideas you might have. Really appreciate it. Thank you very much for watching. Take care.